Welcome back. So I want here to talk about another big concern, ethical concern about AI systems, which is sometimes called transparency, sometimes explainability, sometimes understandability. And these terms, they do have slightly different meanings, slightly different implications in natural language, but they're often used interchangeably in this literature, which I think is a bit unfortunate. Transparency certainly includes more than just explainability and understandability, because it also includes, for instance, um, availability of the data or the model to inspection. But then on the other hand, someone could say, well, that's a matter of explainability too. So it's a little bit murky, but that's okay. We can work with some of this fuzziness as we go. So this issue has to do with knowledge about AI systems and how they work. And because knowledge is so important to us for so many, different things ethically, like can we trust the thing? Is it accurate? Is it justified? Can we fix it? Can we improve it if we need to? Then this issue of transparency also is going to be, very broadly relevant. It's relevant in a lot of different domains. So transparency is good, not just for one reason, but for many different reasons. Now, some of the literature on transparency has made useful distinctions. So one is between at least three types of criteria that we might use to measure transparency. So we might be interested in um, whether the degree of openness or explainability of a system improves its success. So we might use, the success metrics more generally as tests of transparency. We might test whether humans feel that they understand the system, whether they say they understand it, for instance, in a survey. And so that would be a case of the second kind, the human grounded. Or we might provide some kind of more precise measurement, a metric, kind of like the fairness metrics that were discussed previously, that's fed by observable data points. That is, that we somehow can get an quote unquote objective measure of how transparent a system is. So these are sort of three broad approaches we might take to like deciding or measuring whether a system is transparent. And another nice typology is between dimensions of transparency. And so Lipton notes that, one thing we might expect if a system is transparent or explainable or understandable is that the people who are interacting with it can simulate what the system is doing. And by that, he means they can kind of go through it in their mind. They can, talk through the steps of what the system has done. They could draw a model of what the system is doing. So if they can kind of go through the same set of processes themselves or describe basically those processes themselves, then they can simulate the behavior of the system. That means that they understand the system. That's at least a component or a measure of their understanding of the system. Another is whether they can break the system up into its relevant functional parts. Can they say what the different components are that go into the functioning of the model? That's decomposability. And then third, can they understand the way that the model functions at an algorithmic level? Can they understand the the mathematical transformations that are going on in the system? And finally, it's very common to describe AI or ML systems as falling on a spectrum between the transparent and the opaque. And in the article that was assigned as an optional article, Bell and Papantonis, they make much of this distinction. They call opaque models black box models. So, an example of a more transparent type of model is a decision tree, something like the heuristic, well, not heuristic, excuse me, the trees that were used in the symbol processing program for finding solutions, search trees. Okay, search trees are pretty transparent. You can look at them sort of at an overview and understand how they're functioning, what they're doing, why a particular input leads to a particular output, according to the rules of the system. On the other hand, neural networks, at least deep neural networks, neural networks with multiple layers, they tend to be more opaque. They're harder to understand in terms of why they're making the predictions that they are. And so these are more black box models. Now, in order to enhance the explainability of the opaque models, so the transparent models are sort of more explainable or transparent on their face. But the more opaque models, we sort of need to somehow be able to enhance their transparency. One way would be to get better at looking inside them and interpreting what we see. But that often seems to be a really high bar. Like it's too hard to do for these complex neural networks, for instance. And so one of the strategies that's been adopted is to develop post hoc explanations. These are explanations that are offered sort of from the outside in on the system. So they take the systems, they look at over the full set of the system's inputs and its outputs, and then they propose an interpretation of why the system is behaving in the way that it is. So there's a really nice chart in the Bell and Papantanis article that classifies AI systems along these dimensions and notes that the post hoc explainability methods are applicable both to the opaque models and to the transparent models, if needed or if desired. And so this is a nice breakdown. Now I'm going to talk a little bit about Lime as a good example of how these post hoc explainability methods work. But there are a number of others, and SHAP is another very commonly used post hoc explainability method that works similarly to Lime, but I won't go into the details about it. So LIME stands for Local Interpretable Model Agnostic Explanations. So these are explanations that basically work from a set of inputs and a set of outputs. So all the information they have about the system is basically coming from outside the system. They know how the system performs, but they don't know what the internal architecture or behavior of the system is at all. And what they try to do is they try to look at correlations between the inputs and the outputs and then construct explanations of which inputs seem to be especially relevant or predictive of which outputs. And then they give their Lime's output is basically this kind of proposed explanation of the system's behavior. So this can be done with text. Take, for instance, a AI/ML system a neural network that predicts what disease someone has from their symptoms. Okay, and so the only thing that Lime would have available, Lime doesn't have to be able to, in fact, wouldn't be able to, in the normal way that it's applied, look at the weights on the connections between neurons in the neural network. All it would have is information about which sets of symptoms were, led to which diagnoses by the AI system. And it may have, 10,000 or 50,000 examples of sets of symptoms and prediction made by the system. And then it does its thing. It does its, mathy thing and picks out which symptoms seem to be especially correlated with which diagnostics. And then it tells that to the user. It says, okay, we think really what led to the classification of flu in the instance of this particular decision was these three labels: sneeze, headache, and no fatigue. So weight and age weren't really relevant, but sneeze, headache, and no fatigue seem to be the ones that are generating or are mostly responsible for generating that prediction. Okay, now this is model agnostic because it can be applied to a neural network as well as a decision tree, as well as any kind of AI architecture, a Bayesian network, whatever the inner architecture is, Lime can be applied to it. And it's local because it's explaining individual decisions. It needs information about a larger set of decisions to make those local interpretations, but the output that it gives is, explaining individual decisions, or at least proposing an explanation for individual decisions. Lime can also be applied to image classifiers. So, you see this image of a dog playing a guitar, and it works the same way. Lime is basically, looking over a large set of images and how they were classified. And then it makes a guess about what parts of the image are especially relevant to the classification. And so here it's giving you the part that's especially relevant to the electric guitar classification, the part that's especially relevant to the acoustic guitar classification, and the part that's especially relevant to the Labrador classification. By the way that a lot of these classifiers work is they actually output they output scores for a number of possible categories that the image could be in according to the algorithm. So it's sort of telling you like, oh, there's some large percent chance that there's an electric guitar here. It's sort of saying, I think there's an electric guitar at a rate of about 32 points. I think there's an acoustic guitar at a rate of about 24 points, and that there's a Labrador at a rate of about 21 points. Okay, so what Lime is doing is then giving you the parts of the image that, based on its interpretation, Lime's interpretation, seem most relevant to classifications of that type. They're the parts of the image that match the way that parts of images were classified across the much larger data set of 40,000, 50,000 classifications. And so it's again a local explanation because it's telling you why this particular picture was classified in the way that it was. And it is model agnostic because it can be applied whatever the inner architecture of the image classifier is. If it's a CNN or it's just a regular ANN or something else, it doesn't matter. It's model agnostic in that sense. So this is a nice little chart that was produced by DARPA. It's a breakdown of different AI architectures across the axes of explainability and accuracy. And sometimes it seems like there's a trade-off between these. So neural nets can sometimes be highly accurate, but they are also pretty opaque. They're hard to understand. Decision trees, on the other hand, are very easy to understand, but they're often much less accurate. And then there are some other types of architectures that are somewhere in the middle. So there seems to be this trade-off between explainability and accuracy. And this leads to a couple of discussion questions. And so the main one I want to leave you with is, how much explainability would you trade for accuracy, and vice versa? In other words, how important is it to you that you understand why a system is making the decisions it is, as opposed to like being, having a system that makes better decisions? If you have to choose between a system that makes better decisions that you just don't understand and a system that doesn't make as good decisions, but at least you can understand why it makes the decisions that it does, where do you put yourself on that spectrum? So that's the question for reflection I'll leave you with at the end of this summary of transparency issues in AI.